Please Look Up is recorded at SciTech on Wajak Noongar land. Good evening, everybody, and welcome to a special episode of Please Look Up, a podcast produced by Particle. In this episode, we'll be taking a deep dive into the Murchison Widefield Array. My name is Leon, and I'm joined by a man of great impressive titles, the Deputy Executive Director of the International Centre of Radio Astronomy Research, as well as the Director of the Murchison Widefield Array, Professor Steven Tingay. Thank you for being here.
Yeah, no worries.
So we've got you on here today because there's big news in the world of radio astronomy recently, which is that the MWA is turning 10 years old. Mm-hmm. Are you able to tell us a little bit about that? I've even just started calling it the MWA, but what is the MWA?
Yeah, the MWA is a radio telescope based here in Western Australia in the Murchison region, which is Wajarri Yamaji country. It's a precursor telescope for the much bigger Future Square Kilometre Array. Probably many people have heard about that. That's a multi-billion euro international project to build the world's biggest radio telescope here in WA. So the MWA plays a role as a precursor, both in terms of preparing our community to do the science with the SKA, but also to develop the technology and understand how to operate large-scale telescopes in what is a pretty harsh environment out in the Murchison.
Yeah, absolutely right. There's a very broad answer there. And yeah, you've touched on it's a precursor to the SKA, which I'd love to come back to soon. And you said you're sort of preparing the community and the science organisation, the scientific community to operate such a large telescope like this. Is this unique in that sense?
It is a little bit. So the MWA is an international project in itself. There are well and truly upwards of 20 institutes and organisations, universities in 5 different countries around the world working on the MWA. So Australia, Canada, China, Japan and the US. So they all have an interest in preparing for the SKA. And so all of those member countries are sort of chipping in to develop and build and operate the MWA. So it has a pretty different vibe to most facilities that are generally built by a single jurisdiction and operated by a single organisation.
Now I'm going to throw an interesting word at you, Gulgamanu. Can you tell me about that?
Well, that's the Wajarri name for the MWA, and the loose translation is ear that listens to the sky, which is really nice because the picture I have of the MWA is this, as you said, spidery-like antennas distributed over the landscape, shining in the sunlight, just sort of existing quietly on this ancient landscape that has been there for millennia, just quietly listening to what's going on in the universe. So it's a really nice Wajarri name.
That is a really nice name. And what's the relationship between the MWA operators and the observatory and the Wajarri Yamaji people?
Yeah, it goes back a fair while now. The MWA is basically the impetus behind me and others working around Geraldton and around the Midwest. And back in 2009, which was the International Year of Astronomy, we had a project meeting in Geraldton, and the City Council invited along some of the artists from Yamaji Art, and they brought along paintings of some of their sky stories.
Wow.
So we started talking about the Seven Sisters and the Emu in the Sky and other things, and the discussion got really interesting really quickly. And before we knew it, we were travelling out on country together, sitting around the campfire, staring at the sky and sharing our stories.
That's fantastic.
Yeah, thinking about some of the similarities between Indigenous views of the night sky and sort of the Western or Greco-Roman mythologies, as well as the astrophysical stories. So that really took off, and over the last 14 years, we've done multiple global exhibitions of art. We've done a movie for the Dome format called Star Dreaming.
Yes.
And we're cooking up new projects all the time. So it's been amazing to work with the guys from Yamaji Art and to spend some time on country with them and do some amazing things.
Yeah, that's great that it's a continuous ongoing relationship. Like it's not just a symbolic handshake at day one and then that's the end of it.
Absolutely not, because we could not do what we're doing out in the Murchison without the permission and the goodwill of the traditional owners of that land. So it's really, really important for us to deeply respect that. And that's actually natural and easy because we bond over our different views of the same sky. So we share that sky. Nobody owns it. We all have stories. And yeah, it's inspiring to me when we get together and talk through some of those things, and it leads to other conversations as well, and leads to a deeper understanding.
What a great way of looking at it. And I love that sentiment that the shared sky that belongs to nobody. So yes, it's a really great relationship. I really like that. And when we talk about this telescope, so it's a radio telescope, hence why we've got, we mentioned ICRAR earlier there as well. Radio telescopes, looking at photos of the MWA, it doesn't look anything like what you might expect a telescope. I'm thinking of the dish, as everyone does.
Yep.
But this looks like a bunch of spiders.
Yeah. It's an accurate visual description. Pretty interestingly, the MWA is composed of antennas that just sit on the ground, sort of distributed across the landscape. No moving parts. No moving parts. So the steering of the instrument is done completely electronically. I made a really nice little video that shows exactly that the MWA set of antennas is exactly equivalent to the dish, for example. So all of the physics of how a radio telescope works is the same, but many of the functions that are performed in a big dish mechanically and using mechanical engineering are all done electronically with the MWA.
Okay, and what's the choice for that? Why not just build a big dish?
Yeah, well, there's a limit to how big you can build something for a sensible amount of money.
Yeah,
so around about the biggest single radio telescope you can build and not bankrupt yourself is around about 100 metres in diameter. If you want more collecting area and therefore sensitivity and a bigger extent, which means better resolution, a really cool way to do that is to break up your antenna into little bits and scatter them around. So you make more telescopes that are smaller, and that turns out to be much cheaper and much more flexible.
And that's essentially, when you add it all back together, the equivalent of making just a single big telescope.
Yeah, exactly. And you have the freedom to distribute things as you want and configure the telescope according to whatever your requirements are. So introduces a lot of flexibility.
Fantastic. And how many of these antenna does the MWA comprise of?
Currently, the MWA comprises of 8,192 individual antennas, and they're distributed over about 30 square kilometres.
30 square kilometres, okay. But obviously they're not occupying the complete space. How large is each individual antenna?
Individual antennas are about 50 centimetres wide and 50 centimetres tall.
Oh, so they're quite small.
They're very, very manageable. So very easy to deploy, very easy to manufacture. You can manufacture a lot of them very cheaply, and therefore you can get a really sensitive telescope by building lots of antennas at a very reasonable cost.
Much cheaper. I see what you mean, rather than trying to engineer a gigantic dish.
Yeah.
8,192, that's peaking is a power of 2, isn't it?
Radio astronomers do love our powers of 2.
Was that just for convenience, or does that have something to do with the design of the telescope as well?
It sort of comes about through, we quite like the fast Fourier transform in our signal processing, and powers of 2 are quite good. So powers of 2 sort of catch on.
Yeah, man. No, that's good. Oh, it's been a while since I've done the fast Fourier transform, but yeah, okay, I can make a connection there. And so I suppose because it's so vastly different, most people would have little difficulty in imagining how most telescopes work, where you have the focusing of light and collecting that. But when you've got these antennae that look very much like spiders, physically what happens? The light wave arrives at an antenna, and then how is that then turned into a signal and information? Yeah,
so as you say, people can visualise pretty easily what a dish is doing. It's the same as a magnifying glass lens. When the radio waves hit the surface of the dish, they hit some of the surface first, the outside bits, and they're reflected back to the focus. And so the dish structure allows the introduction of delays between the different signals that are hitting the dish. It brings it all to a physical focus. The MWA does that purely electronically. So when a radio wave sweeps across the array, we can adjust the time the signal then takes from each individual antenna, and we can adjust that so that all of those signals add up to a focus in exactly the same way as a dish forms a focus. But instead of a physical delay introduced by the surface of the dish, we have an electronic delay.
Right. So is my understanding, if you've got, just let's keep it simple, 2 antennas, and a light wave comes from space, it will reach one of the antennas a fraction of a second before the other one.
Yep.
And so you then build in an electronic delay into that first antenna.
Yep.
So that by the time you put all the signals together, they are, quote, at the same time.
That's exactly right. So in radio astronomy, we call that it's bringing into focus. You're focusing the instrument, or you're making those signals coherent so they all add up together.
Coherent, is that a very deliberate choice of words?
Yeah, so that refers to the coherence of the radio waves that are just waves. So if you think about waves, you want all the peaks of the waves lining up, and you want all the troughs of the waves lining up. So
I see, yeah.
That means they're incoherence when you do that.
Yeah, okay, that makes sense. Yeah, gotcha. And what frequency does the MWA look at?
It's a what we call low radio frequencies. So the MWA operates between about 80 megahertz and 300 megahertz. So for context, the FM band that you listen to in your car is between sort of 87 and 108 megahertz. So the MWA covers the FM band and a few other well-known bands as well.
So you can pick up the radio station at the MWA if... in theory.
Well, we can. The choice of the Murchison is purposeful because very low population density. It's quite remote, and you want to be away from FM radio stations. You want to be away from cellular phones. You want to be away from people, basically. But we can still spot Geraldton transmitters just over the horizon. So even from the middle of the Murchison, you can pick up those signals with a very sensitive telescope.
Wow, because I imagine sticking a radio tower out there is the equivalent of shining a torch into your eyeball while you're looking in a telescope.
Yeah, exactly right.
And where does this frequency band compare to like Wi-Fi and Bluetooth? Is that anywhere near MWA?
No, they're typically significantly higher in frequency, sort of in around about the gigahertz, multiple gigahertz range.
Like an order of magnitude.
Yeah, orders of magnitude.
But that's fascinating that you're still collecting signals from Geraldton. So is there no radio communication allowed within the Murchison area?
Well, there's on the site, because it is quite remote. There are situations where mobile communications are allowed, and that's through just VHF radios, walkie-talkies basically. But if you take your phone out there is zero signal. Normal communications just aren't possible out there.
Yeah, okay. And yeah, we're kind of just tossing around Murchison quite casually. Whereabouts roughly, if I'm going to drive to Murchison, how do you get there?
To get there, we would typically fly to Geraldton from Perth and then get some four-wheel drives and take the drive out. So it's about 3.5 hour drive. So we head out past Mullawa to a tiny little place called Pindar, and then you chuck a left and you leave the bitumen and you spend the next 250 kilometres on a dirt road.
On a dirt road, wow.
Yeah, and so we end up at Bullardy Station, which is the site that the telescopes are being built on.
Yeah, okay, I gotcha. And that actually was another question I had in mind. Yeah, we're out in this very remote environment, which is obviously exposed to the elements and all that sort of stuff. What sort of physical maintenance does the telescope require?
The MWA is pretty good, actually. Because the antennas are so simple, they're made of aluminium that doesn't really oxidize. The electronics attached to the antennas are pretty simple, and over the course of the last 15 years, we've iterated the design so that they're very robust to the weather and the elements, temperature fluctuations, all those types of things. So what's actually out in the field is very, very simple. Where all the complexity and all of the The cost comes is on the back end, where you've got to deal with the enormous amount of data, all of the computers, all of the, largely speaking, most of the electronics, is inside a big central building that's obviously highly protected.
Yeah, gotcha. Is that central building on site, or are you talking about down here in Perth?
Yeah, it's a central building out on the site, and so all of the signals from the antennas end up in that building. That's where they're all combined and brought into focus.
I see.
Using that technique that we discussed earlier. Mm-hmm. And so the first stage data processing occurs in that building, and we use a large cluster of pretty powerful server computers that have the latest and greatest GPU cards in them.
So you do a little bit of basic processing on site, and then that data, I understand, comes down to Perth. Is there like hundreds of kilometres of fibre optics? Is that what happens?
Yeah, the processed data hit a dedicated fibre optic network that goes, roughly speaking, the 800 kilometres down to Perth, and all of those data are ingested into the Pawsey supercomputing centre, and so that's where our data archive sits, and that's where we've accumulated over the last decade about 47 petabytes worth of data.
47 petabytes.
A lot of data.
That's 47,000 terabytes.
Yeah.
Yeah. Okay. So the laptop I'm using in front of me has about a terabyte.
Yeah. It's the numbers don't mean a lot to many people, but so I use analogies, and my latest one is that if you started Netflix on HD streaming when Constantine the Great was the Roman emperor in the year 300, you would have 47 petabytes by now.
So streaming Netflix for 17 centuries, basically.
Yeah, all the way through the Middle Ages, Dark Ages, Renaissance.
Yeah, that's a good analogy. I like that.
It is a good analogy.
And is there any upper limit? Are we just going to hang on to all that data forever, or...?
Yeah, we're at the point where we actually have to manage that a bit. So over the years, we've accumulated more storage capacity at Pawsey, but we are at the point after a decade where not every single byte of that data set is useful. So we're going back and we're getting rid of some of the less useful stuff, some of the test observations, just so we can free up a bit more space for what comes next. Yeah,
okay, that makes sense, which I'm guessing might lead into SKA as well, which I'll get to in a second. I just wanted to go back to the physics. Essentially, you said between about 80 and 300 megahertz is the frequency. What sort of physical processes produce radio waves of those frequencies?
There's a few different physical processes. Probably the main one is something that we call synchrotron radiation. So this is where you have a magnetic field interacting with charged particles. Generally speaking, in the astrophysical sense, they're electrons. So you have electrons sort of attached to the magnetic field lines, and they spiral around those field lines. And a spiraling charge is accelerated, and accelerated charges produce photons. So in this case, they're radio photons, they're radio waves. So magnetic fields are ubiquitous all through our galaxy, all through other galaxies. So the majority of radiation that we observe from the universe is this type of synchrotron radiation.
Right, and mostly associated with magnetic fields, or are there other sources that can produce synchrotron radiation?
Synchrotron radiation is magnetic fields and charged particles, but there are other processes as well.
Yeah. Okay. Because I was just thinking, I understand the role of magnetic fields in galaxy evolution is still a very open area of research.
Yeah, it sure is. It's something that's still pretty unknown, the origin of magnetic fields and how they operate astrophysically in a lot of different environments. So it's one of the big questions that we hope to answer with radio astronomy.
Yeah, absolutely. And I suppose to follow on that as well, where we talk about how as the universe expands and what light is in the universe gets stretched out, are there any other physical processes that may once have been very high energy but have now been stretched out into the radio waves that we can still detect?
Well, the radio waves that were produced from first generation of stars and galaxies forming, so back in the very early universe, first billion years after the Big Bang, largely speaking, there was a lot of neutral hydrogen. That neutral hydrogen produced stars and galaxies eventually. But neutral hydrogen also produces radio waves through a changing configuration of the atom. And it produces radio waves at very specific frequency, 1.421 something gigahertz.
Mm-hmm.
And so actually the MWA and the SKA are designed to tune into that radio emission, but after it's travelled all the way across the universe, it's been reduced in frequency by a factor of 10.
Right.
So it starts at 1.4 gigahertz, and we receive it at 150 megahertz.
Yeah, smack bang in the middle.
Yeah.
Right. So you can map neutral hydrogen across the entire universe, basically. Well, the more distant reaches, I should say.
In the really distant universe, and the point is to watch that neutral hydrogen changing and forming the stars and galaxies. So when it's forming the stars and galaxies, those stars and galaxies produce ionizing emissions, so photons at higher energy, UV, X-ray. And as those high-energy photons propagate out from the stars and galaxies, they ionize the neutral hydrogen.
Right.
So the neutral hydrogen sort of disappears, evaporates, sort of. The stars and galaxies appear, and the universe becomes transparent.
Yeah, okay. Is this epoch of reionization? I've definitely heard about that. And it's still very, I think poorly is the right word, but there's still a lot of understanding to do with regards to that area.
Oh, absolutely. I reckon there's probably 2 or 3 Nobel Prizes in the people who figure out the epoch of reionization and all the astrophysics around it. It's the last really unexplored epoch in the history of our universe, that sort of first billion years. So that's big science, and that's why we build things like the MWA.
Absolutely. And you've mentioned that coming into sort of bringing it all to today, where you've said the MWA is a precursor to the SKA, the Square Kilometre Array. Is that basically taking the ideas and lessons from MWA and scaling it up and making this magnificent, all-powerful telescope?
Yeah, that's right. So the SKA is such a massive leap from the capabilities of telescopes that we had a generation ago. You need a stepping stone in between. So the MWA and other precursors around the world play that role.
Gotcha.
So it's a chance to learn how to calibrate and make images from, as you described earlier, pretty different type of telescope, and for the community to take the first really serious swing at some of this science, like the epoch of reionization. So this is all preparation for the SKA.
Right. And so are you able to quickly give us a rundown of the SKA for people who don't know what that is?
The SKA, or Square Kilometre Array, is a big version of the MWA.
I think that's the best way of putting it.
Qualitatively, it's a large number of relatively simple antennas, no moving parts, scattered out around the landscape. But this time it's like 131,000 antennas, not 8,000.
Right.
And it's distributed over 1,000 square kilometres, not 30.
Right, so significantly larger.
Much more sensitive, potential for much more detailed images. Yeah.
Yeah, and sensitive enough to potentially see into this EOR.
Mm-hmm.
Yep. And in your role itself, your day-to-day role, what's your involvement with that project or with the MWA?
Well, I'm the director of the MWA, so responsible for leading the team that built and now operates the telescope. So that's been enormous amount of fun over the last decade. And alongside that, me and my team have been deeply involved in the SKA development. And in fact, the MWA has hosted over the last decade several generations of prototypes for the SKA antennas, testing the configuration, testing sensitivity, performance, understanding how those antennas survive in the environment. And so all of that work has been wrapped up, and that's gone into the construction program now. So we've done an enormous amount of design work for elements of the electronics. We've done a huge amount of prototyping and testing of the different designs, and all of that has fed into the construction program, and ultimately that is being expressed in a bunch of quite high-value contracts that are going to go to Australian industry.
Wow.
So you sort of close the loop, and there's a economic as well as scientific benefit to these projects in that sense.
Yeah, and that's interesting because that is always often a case of for people who are in it for the science, you have no problem in dedicating time and effort to a project, but a lot of questions are always hanging over industry and economy and things like that. And so you're saying that, yeah, there's a lot of money going into the Australian industry because of this massive scientific project.
Yeah, a couple of years ago, I commissioned an an economic and social impact assessment of the MWA project. And the people who did that assessment discovered that for every dollar that Australia has spent on the MWA, more than $2 of GDP has been generated.
Wow.
So that's, that people don't think of telescopes in that way.
No, not at
but that's
all.
comparable to sort of bridges or all sorts of other bits of infrastructure that are more standard in people's thinking. So, I think it's important to make sure we pursue amazing science. But in doing that, we have to really push the envelope, and that means that we need to get industry involved, and that feeds back into their capabilities as well.
Yeah, I can see what you mean. And that's such an impressive number as well. So basically you painted a really nice picture of the MWA as being both a stepping stone to SKA, something much larger, but also by itself an incredibly capable and versatile piece of equipment. Mm-hmm. So it really is a fantastic piece of technology. I suppose we'll come back to the MWA. What are some of the, in your opinion, what do you think some of the most exciting things that it's discovered?
Just last week was published a paper by one of our researchers, Natasha Hurley-Walker, and her discovery of, it's a second object of this type that she and her team have discovered, but what appears to be a compact star in our galaxy that has produced bursts of radio waves every 20 minutes or so for the last 30 years. So it's possibly a neutron star or maybe a white dwarf star that has a magnetic field and is rotating. And it's a little bit of a mystery because it doesn't look like it should be powerful enough to produce these radio waves, but it does. So it's a discovery of a completely, apparently new type of object in our galaxy. So that was published in the journal Nature last week, which is sort of the most prestigious journal in the world. And Natasha had the first one in Nature last year. So, I'm expecting one per year from Natasha from now on. If you're listening, Natasha, no pressure.
You said that the data went back 30 years. MWA hasn't been around for 30 years. So
no.
You just found something in the data and then went looking for historical records? Is that what happened?
Yeah, exactly. And this is a really super interesting part of the story. With the MWA, as I said before, we have 47 petabytes of data. That goes back about a decade. So Natasha and her team were sort of sifting through some of the current data and decided to look for things that vary in brightness. And so then they found this. So the obvious thing to do is to look back through our archive, and she kept finding it through the archive.
Oh, wow.
But then she went to the archives of other telescopes around the world and found it in those archives as well. So it really dramatically shows the value of keeping your data.
Yeah.
Because the idea that you have that maybe motivated the collection of the data, after a decade, maybe your ideas have changed, maybe new things have come up. And if you've got the ability to go back in time and re-look through that archive, it's a goldmine. So who knows what else is in there?
Yeah, that's a fantastic sentiment. And I guess the same thinking applies to the SKA as well. Mm-hmm. There are certain science objectives to the project, but any number of things that we haven't even thought of that we may one day discover. Now, you mentioned that the Pawsey Supercomputing Centre is storing about 47 odd terabytes of data from the MWA. Is that a common thing? Do all research organisations store and catalogue their data like that?
It's pretty common. In fact, under legislation, you're supposed to keep all of the records for the data that you use for producing publications and all that sort of stuff. So there's lots of laws about retaining information. So it is a common thing amongst telescopes is to store all of the data that comes from the telescopes in an archive. The difference with the MWA is that the amounts of data produced are absolutely enormous. So 47 or 50 petabytes represents about 1/6 of the absolute total amount of research data across the entirety of Australia, across all disciplines. So that just one project takes up 1/6 of that volume, which is huge.
Wow, so about 300 petabytes of scientific data in the entire country for a ballpark figure, and 1/6 of it is the MWA.
Yeah, that's right. And it makes up a much bigger fraction of the data that's actually properly archived, that has proper metadata, that's discoverable, and people can actually access. the 300 petabytes is a bit of an estimate based on what we know and an extrapolation.
Oh, okay. And it could just be sitting on someone's hard drive and things like that.
Yeah, exactly. A lot of data is not all that well curated. It's a fair bit of effort and a fair bit of cost to go through that properly. But as we described earlier, the benefits of doing that are sometimes not apparent until years after you've made those observations.
Yep. So if 300 petabytes is the estimate of data, is there an estimate of like usable data that has been properly catalogued?
Yeah, I think it's sitting at around about 70 petabytes or so, and most of that's astronomy.
Yeah.
So astronomers,
lots of data.
Leading edge of looking after their data.
And so of those 70, about 50 is MWA. So it
Yeah,
went from being 1/6 of the total data to being 5/7.
Yeah, approximately. Yeah. It's a big fraction.
Yeah, wow. And as you say, and it goes to show long-term benefits. It is worth investing in the time and energy now because you can always come back and you never know what you're going to find.
Yeah, exactly.
I understand MWA is also quite good at just seeing large numbers of galaxies because it has just an extremely wide field of view. Is that right?
Yeah, the hint's in the name, Murchison Widefield Array, and the wide field, the word wide field refers to the field of view of the telescope on the sky. So if you look at the MWA, you'll see that our antennas are grouped into groups of 16, what we call a tile.
Yeah.
And that is sort of the primary antenna system. So that antenna has a field of view of maybe 1,000 square degrees, which is a lot compared to any other telescope in the world.
Yeah. So for comparison, I remember the full moon is about half a square degree, I believe.
It's something of... It's like a quarter of a square degree or something like that.
Yeah, so we're talking many times the size of the full moon.
many thousands of times the full moon. So when you look out into the universe, you get everything that is in that field of view. So thousands and thousands of galaxies and stars in our galaxy. So it's a really efficient way to do that. As I said earlier, you pay the price on the back end where you've got to store the data and process the data.
Yeah, gotcha. Right. But yeah, as we also see, you can go back through that data decades later and still find amazing things.
Yep, absolutely.
Which leads to, I've got still just a few more questions. How many papers have been generated by the MWA in some way or another?
I think it's pretty close to, it's over 200 by now.
Wow.
I'd have to go back and check exactly, but it's certainly in the hundreds. And some of those papers have had enormous numbers of citations, which is sort of the key metric in academia. It's not how many papers you produce, it's who is referring to your papers, and that's sort of the judgment of quality. So it's been enormously scientifically productive. It's supported the training of many dozens of graduate students, so PhDs and master students. It's supported lots of activities for undergraduate students. That's sort of a key role in preparing our community for the life of the SKA down the track. So it won't be people of my age who are leading the science in the SKA, but it's the people who are my PhD students at the moment.
And how many people work with or at the MWA at the moment?
The core operations team is astonishingly lean and mean. So the entire facility is operated by 5 or 6 people at Curtin University.
Wow. So
they are the people actually paid to operate the MWA, keep it alive, look after the data. But the user community for the MWA is in excess of 500 researchers from all of our member countries around the world. So once the data go into the Pawsey Centre, our users can go to that portal, discover the data that they want, download it, and so they're the people who process the data and write the papers. So in that sense, it's in the hundreds. And then after 18 months, all of our data become public. So anyone anywhere in the world can grab them and do something. And so there are probably more hundreds of researchers around the world doing that.
Everyone just getting their hands on the data. And it is interesting that you mentioned that such a small team of core operators, because I guess one of the things that most people don't realise is that modern astronomy is not done by sitting at the telescope and looking through it. These hundreds of users, do they just put in a request for time and then the telescope automatically does it and then they just download their data?
Yeah, twice per year we issue what's called a call for proposals, and anyone can write a proposal with a project idea. They get assessed by a panel. they recommend the ranking of those projects, and then if you're high enough ranked, then your proposal gets scheduled. So it goes into the queue, data are collected, and away you go.
And away you go. Do you yourself do much research these days?
Yes, I do. One of my key personal metrics is to try and produce at least one first author publication per year.
It's an admirable goal.
It's an admirable goal, and I tend to stick to it, although I'm looking like I'm in a little bit of trouble this year. But yeah, my passion is astrophysics, and that's why I got into it at a young age. So, the day that I have to give that up is the day that, I'll stop doing it.
That's hits it on the head, I think.
But my research is done between the hours of 10 p.m. and 2 a.m.
Yeah, fair. Once you've finished all your other work for the day.
Yeah, exactly.
Yep. And then my last main question, really, sort of diving at the heart of anyone who loves astronomy. What's your take on when you deal with millions of galaxies in a single data set, and you're looking at this tens of petabytes of data? How do you put yourself in the universe? Do you feel small? Do you feel large? Do you feel overwhelmed? What's your personal take on the whole thing?
It's a good question. So I knew I wanted to be an astronomer at like age 6. Because growing up in the country, I would just sit outside at night wondering about what these stars were, where they came from, what does it mean. So from a really early age, I immersed myself in the universe, really. And what I do now as a professional astronomer is really no different, actually. And whether it's like thousands of galaxies emitting radio waves in an image on my screen or sitting outside at night, I find it quite easy to immerse myself in it and sort of visualize what all of that means. I really like looking at the planets and the moon all together in the sky, and you know that Venus is a certain distance and the moon is closer. And I find it really interesting to visualize that geometry and take myself off the surface of the Earth and visualize it from the point of view of the solar system, or the galaxy or the universe. So I don't know, maybe I ingrained it into myself at a very early age, but it's pretty natural to me.
Yeah, right. That's a really beautiful way of thinking about it. Yeah, you're just enjoying the part of it that you're experiencing at the time, and it is what it is. That's a fantastic way to finish, I think. Thank you so much for being here today, Professor Tingay. It's been an absolute pleasure.
No worries. Thanks, Leon.
That's it for this special episode of Particles Please Look Up. We'll see you next month, where we talk about the night sky and the space news for September. If you want to hear more interesting space news, check out the website particle.scitech.org.au for more information.